Ah, okay. Yeah, that's fine, being recorded.
İlhan,
Actually, I got in contact with Berkan, and I think now you are co-host. Can you check it?
How do I check that?
You go to, I think, participants, and
Oh,
you find
participant.
your name, and you
Oh,
click.
yes, co-host. Yes.
Okay, so maybe then I will stop sharing, and
Okay.
you can. That will be easier.
Then I'll have control of the
Yeah,
change.
exactly. I am really sorry again.
No, no problem. Okay. So share screen. That's it. Share. No. I'll make it full screen. Where is it? Under view, I think. Yeah. Oh, is that bigger? Okay, good. Well, anyway, thank you very much, and we like to acknowledge the native, the original inhabitants of this land when we give these talks. So this is Turramurrugal country. Okay, so the problem, as you would have read if you read the abstract, is that I'm interested in when a category F, well, if you define a representation of a category F to be a functor from that category into a category of modules, then I'm interested in when the representations of that category F could be those of a groupoid. So you want equivalence of categories between the representations of your category F and the groupoid or a groupoid. Sometimes the groupoid is just the invertible morphisms in the category you have. That's not always the case, but that's a good starting point. That's a groupoid at least that you can get your hands on. If you have a category F, you just take the same objects and the invertible morphisms, and that gives you a groupoid. And generally, that of course that won't have the same representations as the original category, but sometimes it does, and it's a little bit surprising to me how general this can be. If you split idempotence in the category, that doesn't change the representations, and but it does change the core groupoid. So you can see that the core groupoid is not necessarily the only thing that could work. That might only work after you've split some idempotence. So the two motivating examples, the original one was well, we didn't actually know about this paper when we started. Steve Lack and I started working on Gold-Kahn type theorems, just in a general, to try and get some axioms for when things like the Gold-Kahn theorems would apply. I'll say what that is in a minute, what the Gold-Kahn theorem is. But anyway, this particular result I found in another paper, not the one by Pirashvili, but he seems to be the original person to publish this result. So if you take F to be the category of finite sets and partial injective maps, so that you can think of them as the spans of injective functions between two finite sets. So the groupoid then is just the category of finite sets and bijections, which has various names in different parts of the literature. I write it as a German S because it's the symmetric groupoid. I call it the symmetric groupoid. And so there's this result, which is in Pirashvili, the paper I have indicated up there, which says that the representations of that particular category are those of the symmetric groupoid. Now, the symmetric groupoid is really a co-product of groups, one object categories, which are groups. And so the representations is really the product of all the categories of representations of the usual symmetric groups. And the other thing that got me all excited was this next paper by Nick Kuhn. And it seemed amazing to me because I'd studied the category of, I'd studied the category where you take a finite field and you look at the vector spaces over that field, the finite vector spaces or finite dimensional. It's the same thing in this case. Vector spaces over that finite field, and then you take just the linear isomorphisms, and that's an interesting category. So Andre Joyard and I had a nice monoidal structure on the category of representations of this groupoid, the general linear groupoid over a finite field, and also found that it was braided, and the braiding is not a symmetry. So it was a nice example there, and it's quite hard to prove. It's not so hard to find to describe the braiding, but to prove it's invertible, really you have to learn a lot of the theory of this finite general linear groups.
Sorry, can I ask a question at this point?
Yes, please.
Why is the general linear groupoid? That's just the the groups GLNF, right?
That's right.
Why?
No, the groups GLNF, the general linear groups with the N in there. But
that's what makes it a groupoid. Okay, now I got it.
Yeah, the general linear groupoid has the finite dimensional vector space as its object, so you can just take the dimension if you want as a skeleton of that, and then you take the linear isomorphisms between them. So that is actually the co-product. Well, every groupoid is a co-product of groups thought of as one object categories. And so when you take the representations, you get the product of the categories of representations. But the amazing thing that Kuhn found was, as long as the ring the field that you're taking the representations in, the vector spaces where you're taking the representations, as long as that field has the characteristic invertible in that field, then you've got this equivalence. You've got the thing I'm asking about. You take the category of vector spaces and all linear maps over that finite field, and it has the same representations as just the groupoid inside it, which was a surprise to me. And so that's the kind of result I'm trying to get a kind of theory for. So the original Dold-Kahn theorem, probably people know, the category of simplicial R modules is equivalent to the category of chain complexes of R modules. And that's a nice theorem of Dold and Kahn and Pupa to some extent. I think Kahn did it just for abelian groups as the receiving category, where R is Z or Z. What it turns out that this problem does reduce to a groupoid suffices type problem. This is in a paper of Steve Lack and myself, where you really can reduce the equivalence of the Dold-Kahn theorem to this groupoid suffices problem for the category of simplicial the simplicial category, which the simplicial category has as objects the linearly ordered sets, finite linearly ordered sets, and linearly ordered maps between them. But if you now also take the first element preserving ones, so this delta sub bottom is the category of finite ordinals, linear order preserving maps, which also preserve the bottom element. So I've described that there, okay, in the dot point 2. But so the groupoid here is not very interesting because it's discrete. The only invertible morphisms in this delta are identities. So the core groupoid in this case is just a countable product of copies of your category of modules. V is my category of modules, R modules. Okay, so any questions there? So what I thought I'd do is a kind of baby example to indicate a lot of things that I want to talk about here. So in that category, just pick on one ordinal, namely 3, and take the endomorphisms of 3. So we're looking at order preserving maps from 3 to 3, which preserve the first element. And here there's only these 6 elements in the group, in the monoid. It's only a monoid. I'm writing these as matrices, but they're not meant to be matrices. They're meant to be functions, right? So this iota is the thing that takes 0 to 0, 1 to 1, 2 to 2. So it's the identity function. Sigma naught is the one that takes, everything has to take 0 to 0 because that's the first element. And it still has to preserve order. So you only have these 6 elements. And in fact, the sigma naught and tau or tor generate the thing, and everything's a product of those two. And the relations that they satisfy are that they are all idempotents, sigma naught and tor are idempotents, and these other equations I've got here. This first one sort of is a braid type, Coxeter type thing, but it's a bit stronger than that. And this is only a monoid, remember, it's not a group. We're generating a monoid out of those conditions. Right. So the only invertible element in here is the identity. So we've only got a one object, one element groupoid. And the core groupoid, so the core groupoid of this thing is a discrete category with one object. Oh, did I skip over a page about linearization? Excuse me, I did. I missed this page somehow. Yes. Can I go back? I'll just go back quickly because the important thing is that we're wanting to linearize the HOMs in each of these categories we're looking at. So if you've got a category, you can always take the HOMs as a basis for a vector space, and so you just take the category that you get, which becomes an additive category. It's got, you can add in the HOMs, each HOM is a vector space over R, or a module over R if R is just a ring. And so that's what I'm writing as RF. You could write R sub star F or something like that, but it's the free V category, meaning category enriched in modules. So if you're looking at the representations which are now additive functors from RF into V, it's the same as it's equivalent anyway or isomorphic actually to the original category of representations of F. So you can pass, we want to deal with additive categories rather than all categories. So that's why I'm wanting to linearize everything. Yeah, so Steve and I, so in terms of additive categories, I think of an additive category as being a ring with many objects. or an algebra with many objects. So there's a Morita theory for those things. So the question I'm looking at is kind of a Morita theorem, but these categories are only special ones because they're not general additive categories, they're free additive categories on just ordinary categories. And so it's a Morita theory of those things from sort of an additive category point of view. Yeah, so I'm sorry I missed that page. I should be changing with the things on the on the typewriter rather than on the keyboard rather than with the mouse. Okay, so that's the reason I'm writing R. So this delta bottom of C is a monoid. So when you linearize it, you get an algebra, possibly without identity. But of course, it has identity because in this case, we're starting with a monoid, which has an identity. But if you leave out the identity, that's what I'm calling delta prime. Just by leaving out the identity, it turns out when you linearize, there still is an identity, but it's not the identity of C. And it's this particular combination of sigma naught plus sigma 1 minus epsilon. Anyway, that's I don't expect you to see why that's true, but it is true that you get an identity element even if you leave out the original identity, and that's a strange phenomenon which comes up here. So I'm continuing on that example to see why the representations of this monoid, once you've linearized it, so now we can add and so on in this algebra now. You have a complete list of orthogonal idempotents. These things turn out to be orthogonal idempotents. There's a technique for discovering those things, but I'll just pull them out of the hat. And now I want to not only split idempotents, but also adjoin direct sums, because that doesn't affect the representations, because those direct sums and splitting idempotents are preserved by all additive functors. Idempotents are preserved by splittings, are all preserved by all functors, and the direct sums are preserved by additive functors. So because we've got this complete set of orthogonal idempotents, the C in this category, the original single object, breaks up as a direct sum of four things. One, the idempotent splitting those idempotents. So they were endomorphisms of C, and so you split them, and you get C as an isomorphism, as isomorphic to a direct sum of four things. But it turns out that E1 and E2 are actually isomorphic, and you can see that by looking at various relations, that the gamma actually takes the splitting of E1 into the splitting of E2, and then the delta is the inverse for it. It takes the splitting of E1 into the splitting of E2 into the splitting of E1. So and they are mutually inverse because of that gamma delta is equal to E1 and delta gamma is equal to E2. So gamma restricts to an isomorphism between E1 and E2. And so actually we've got that C is a direct sum of only three things, one of them being repeated. Okay, that's maybe I don't expect you to see all that straight off, but I'm just trying to assert it a bit to show you this case. So now I want to transport the sigma naught, sigma 1, and tau across that isomorphism. And so sigma naught transports to a matrix. These are matrices now. These are not functions. These are 4x4 matrices as maps between the sum of direct sum of four things. And so you have sigma naught, sigma 1, and tau giving you these three things. And if you check what happens for an endomorphism of that direct sum to commute with all those three matrices, then that forces the thing which could be a sum of four different functions to be a sum of just three, really, but the two, it's just a repetition. So it turns out that this algebra is the V Morita equivalent to the free R module on the discrete 3. I wrote boldface 3 before, that was an ordinal. Now I'm writing just an ordinary 3 for discrete 3. So in other words, the representations of this particular thing is just V cross V cross V. So that's the kind of thing that's going on here. And I want to try and give other examples, but oops, oh dear. Yeah. So I'm trying to look at what structure on F allows this to happen. And we've got that good example of Kuhn where F is a category of vector spaces. So it's a fairly good category. And maybe you've met factorization systems before. These are the canonical examples. E, the script E, consists of the epimorphisms and M of the monomorphisms. They don't always form, in any given category, they don't always form a factorization system, but okay, so E is a class of maps and M is a class of maps. Thinking of M's as kind of special monomorphisms, E's as special epimorphisms. And the axioms for a factorization system are that if you take an M and compose on one of the sides with an invertible thing, it's in M again. If you take something in E and compose on the other side with an invertible thing, it's also in E. The second property is if you have a square, commuting square in the category, where the top thing's an E and the bottom thing's an M, then there's a diagonal going across the square, making the two triangles commute. That's called the diagonal fill-in property, or if you draw things the other way around, it's very popular in homotopy theory now to call it the left and right lifting properties. So yeah, it's just drawing the squares the other way around. And of course, for a factorization system, every morphism should factor as an E followed by an M. I compose in the backhanded way that we compose functions. But it turns out, even though that first thing looks as though you can't compose with an arbitrary M and get an M, it turns out as a consequence that M is closed under composition and so is E. And that the intersection of E and M is exactly the invertible morphisms. So the things that are both E's and M's are invertible. So in general, in any category, it's not true that in a given general category, it's not true that an epi and a mono necessarily make it an invertible. If something's epi and mono, it need not be invertible. But if it's a factorization system, then that is true. And so I'm going to identify at times the E with the subcategory of F with the same objects as F and the morphisms that are in E. So sometimes E will mean that subcategory, and M not just a set of morphisms. And M is has the same objects as F and the morphisms that are in M, because they're closed under composition, and obviously identities are in there as well. And then the intersection is the groupoid we're talking about. It's the invertible morphisms in F. So it's got the same objects as F and the invertible morphisms. I also need this. Remember I said before we left out identities? Well, this is something that the priming process is going to take kind of complements of things. So M prime is going to be the set of morphisms in F that are not in M. And E prime is a set of morphisms in F that are not in E. So these are not subcategories, but these are a funny thing to consider, but that's what I'm wanting to consider. And G prime is the set of morphisms that are not invertible. So we consider that. And we do want a proper factorization system. That means that everything in E is assumed to be an epi and every member of M a monomorphism. so this duality property, that's a nice thing to have conditions that, like for an abelian category, the duals in an abelian category, if you've got a factorization system EM on F, then swap them around and turn the M's into E's and the E's into M's, and you've got a factorization system on F op. So you can dualize any theorems that deal with these kinds of factorization systems. And the main property I need is this property, which is like the property for monomorphisms and epimorphisms that, or injective and surjective maps, that if HF is in M, then F is in M. And dually, if FK is in E, then the second thing is in E. Yeah. Okay, so I told Ilhan that there was a little bit of higher category theory in this, and the higher category is going to be a bicategory, but you don't need to know too much about bicategories to understand this one, I think. So I'm writing this math frac R for the bicategory whose objects are V categories. So that's categories whose HOMs are modules. So bicategories not only have objects and morphisms, they have their HOM category. They have HOM categories instead of HOM sets, and so the HOM category RAB for A and B are V categories is this functor category, the additive functors or the R linear functors from B op tensor A, comma V. So these are like left A, right B modules. So the B op means that you're acting on the right with it and the A on the left. So these are called, I'd rather use the word modules from A to B, because otherwise you have to have this long sentence saying left A, right B modules. So I call these modules from A to B, and that's what they are in this bicategory. The morphisms in the bicategory, the modules themselves. And in this particular case, because our base category V is a nice abelian category, a Grothendieck abelian category, it makes sense to talk about exact sequences in these HOMs. So module composition is just as it is really for modules, tensor product of modules. We've got this fancy notation using an integral, which is called a coend. So if you have a module from A to B, H, and a module K from B to C, then the new module is obtained by quotienting out the B action with the H and the B action with the K. So that's exactly the same as with modules, which are just one object, the one object case. So if you've given two V functors now, you can get a module out of it by, so you've got a functor from A to C and a functor from B to C. You get a module by, which is I'm calling script C GF. It's like a HOM, because you can think of a functor as being a generalized object of a category. And so you should be able to talk about the HOMs between functors into that category. And that's what this thing is. And its value at BA is the HOM of the values of G and the values of F. In particular, you can take one of those functors F and G to be the identity, take G to be the identity, and then you get this thing that's called F lower star. So that has the F going into the covariant variable, and just that leaves the object as the identity in the contravariant variable, and the F upper star is the other way around. So the F lower star goes from A to B, the same direction as F, F upper star goes back the other way. And in the bicategory, as well, Kahn originally noted, that you can express adjunctions between functors as in terms of unit and co-unit, which are just two cells, a natural transformation. So you can express adjunction in any bicategory. So it makes sense to say that F lower star has F upper star as a right adjoint in R. And Levere had an interesting paper on metric spaces using as a motivation for doing enriched category theory. And it turns out that this little fact is very close to Cauchy completeness. So if I was dealing with V being the real numbers or something instead of the category of R modules, R modules, then Cauchy completeness comes down to saying that a module having a right adjoint at all into B is the same thing as being an F lower star or isomorphic to an F lower star. So modules with right adjoints, I like to call Cauchy modules, and ones that come from with this F lower star I call convergent ones. So this is really saying that every Cauchy module is a convergent module. And in that case, that's what it means for B to be Cauchy complete. And in the additive case, it means that you have idempotent splitting and direct sums, finite direct sums. So that's what it means to be Cauchy complete, a bit more concretely. This looks like a big lot, probably too big a page, but roughly what it's saying is that if you're in a bicategory and you have an adjunction, and then you have an idempotent on the left adjoint, say, then there's a thing called mate, the corresponding idempotent on the other, on U. You get a corresponding idempotent on U, because maps from F to F are the same as maps from U to U, back the other way. And that idempotent on U, if you split the idempotent on F, then you get another functor or another morphism, and that will be left adjoint to the splitting of the idempotent on U. That's all I'm saying here, really. So, but it's a little bit more you want to know, because it's just the fact that the idempotent on F is kind of the mate of the one on U. It comes by using the unit and the co-unit. That's what it means. To be for some map of it from F to F to corresponding one from U to U means you obtain it by using the unit and the co-unit of the adjunction. So I won't go through the technical statement of it there, but that's all I'm saying. Basically, the retract of an adjunction gives you an adjunction again, in quick words. That's the slogan. Now, another way of looking at modules is that this is really like when you have a module just in ordinary algebra. You get a module from, you've got a functor out which is tensoring by that module. So that's really what it is. So if you take a module from A to B, using this integral notation, the word kernel gets what they use for kernels of operators in analysis. It looks a bit like that. So from this module from A to B, you get a functor I'm calling H hat from the representations of V to the representations of A, and it's defined by, so every functor is actually a module into the free V category on one, which is the thing that has one object and has R as its hom. And so you can compose using the formula I had before. And so this is the formula for H hat. And so H hat actually gives you a pseudo functor from R op to V cat. That's all that's saying is that for each object of R, which is a V category, A, say, you get the functor category AV, the representations of A, the linear representations of A. And then, but it turns because of the op, it turns a module into a functor around the other way. So our module H goes from A to B, the H hat goes from BV to AV. And that H hat has, because you're using colimits to define it, you expect it to have a right adjoint, and it does. I'm calling that H tilde, and it goes back the other way, and it's just obtained by homming there. It's H tilde of F at B is this just homming process. Okay, so I guess what I'm trying to show is that you might think that this way of getting an equivalence between the representations of G and the representations of F is just going to be obtained by restricting along some particular functor or something, but it's not quite that. You've got to go into the modules. Now, the module will give you now a module, J upper star, and you have a J lower star as well, but J upper star going in the opposite direction from RF to RG. And but that J upper star is not a Morita equivalence. And that's where this lemma comes in. We're going to take a splitting of an idempotent on that on J star. I guess it's a bit technical, but right. So we draw this particular commutative square. So remember, M prime consists of. I'm taking the vector space. I'm thinking of R as a field, so I call it a vector space all the time, generated by R with basis the M prime maps from A to B. That's included in there, included in the R of FAB. And what I'm saying is, remember that in the first variable A and C in that diagram, this A is a module coming where the A comes out of G and the B comes out of F. So G is going to be an invertible thing, and little h is going to be an arbitrary linear thing. And because of the axioms for a factorization system, you get this commutative square. And so now I'm writing a straight M prime to mean the module that comes from this Rm prime. And it's so it's a submodule of J star, J upper star. And so you get this short exact sequence going from 0 to M prime. So the kernel of this Q is the things that are not in M, and so or generated by things that are not in M. So you get this short exact sequence: M prime, J upper star, M. And dually with the E's, you get one from E prime, J lower star to E. And the J upper star and J lower star are adjoint, remember. So now you've got modules in both directions. The M's of the factorization system are somehow giving you something from RF to RG, and the E's are giving you something from RG to RF. And so generally that's not an equivalence. Right. However, there's a lot of, it comes close. What's actually true is that M composed with E is isomorphic to the identity. Now, the identity module is the Hom module. So the identity of a module of a V category is the Hom module. That's It's kind of the innate lemma tells you that that's going to work. So how do you prove that? Well, I'm not going to prove it, but I'm going to explain what it means. So this morphism from M composed with E to 1, the identity module, has got to be made up of things like this phi b. So the phi b. So remember, the things in E, straight E, B, D are linear combinations of E morphisms, and these things in MCB are linear combinations of M morphisms. And so you've just got to take something in E, B, D, and E from B to D, and an M from C to B, and it's basically the composite. You just compose, but you've got to end up with an invertible thing, or so you have to take it to be 0. So that's one of the reasons we had to linearize a bit. You've got to have a 0, and this is as natural as it could be in both variables, in all variables. That's what we call dinatural, or extraordinarily natural in the B variable. That has a meaning in McLean. You'll find it. And it turns out that that this gives you an isomorphism between. This is an isomorphism. And so when you apply hat, so the hat process was contravariant. So it turns, and it's a pseudo functor, so it takes adjunctions into adjunctions and composition and composition. Anyway, it turns the composition around, and so you get that the composite of these functors, E hat and M hat, are actually identity functors. And then when you've got something like that and an adjunction, remember that E hat is left adjoint to E tilde for any module, that the hat's left adjoint to the tilde. You actually get something from M hat to E tilde. So there's some relationship. I'm calling it big theta, the M hat and the E tilde. Now, to show you, there are probably more down-to-earth ways of describing the M hat and the E tilde in good situations anyway, which are helpful. So if you've got an object of F, I'm writing sub A for the sub-objects of A as an ordered set, if you like. Just a set, really. So you can think of them as, because M's closed under composition, that's just the same as the category M over A. But just a skeleton of it. So just take a representative set. So if you've got a realistic category, it might have inclusions. Originally, McLean tried to axiomatize inclusions rather than a factorization system, but this is the better way to think of sub-objects. And a similar thing for the quotient objects. So that's an E out of A is a quotient, an isomorphism class of E's out of A. So I'm writing sub A and quo A for those two sets. And then this M hat of T at A is just the co-product. I'll use sum for co-product of the TU, where the U is the domain of one of these chosen representatives of the sub-objects. And similar thing for E tilde, it's the product of the quotients of the TWs. So when sub A and quo A are finite, which happens in the case of finite vector spaces, then both these sums and products are direct sums. And this theta from M hat to E tilde is quite a natural thing. It's a matrix between these direct sums whose non-zero entries are all the TEMs where the EM is in G. So you have it's a matrix. And if you can actually linear order the sub-objects of A and the quotient objects in A with in such a way that if you've got EIMJ lying in G, that implies that I is less than or equal to J, and that the composite EIMI is 1. This might sound a bit technical, but it can be done, and that's what Steve Black and I did in our Kahn-Dold paper, Dold-Kahn. And then square matrices, they've got identities down the main diagonal, and they're triangular. And so you get an invertible matrix because we've got additive we're dealing with matrices where we're dealing with additive inverses. So you've got minus signs. So for example, the matrix 1, 1, 0, 1 has inverse 1, 1, 0, minus 1, 1. So you need the minuses. Next page. Something strange happening. Okay. Sorry. So this is like the Pirishvili example. If you had any category in which every morphism is a monomorphism, that's like the original category of finite sets and injective functions. And if you have that every slice category has finitely many isomorphism classes, then I'll write F equals A sharp to be the category of spans there. So that's now like in the particular example, partial injective morphisms, functions. And the morphisms are isomorphism class of span. So that's the partial maps. And you compose spans by taking pullbacks. Then M consists of the spans, the spans where the F1 is invertible, and E consists of the spans where the F2 is invertible. It's a nice symmetric way of looking at this thing, theoretically. And the groupoid G, the core groupoid, is the same as the core groupoid of A, because these, it's the same as the core groupoid. And in this case, you do get an equivalence of the type we're wanting. And Steve Black and I proved this using comonadicity arguments. So we looked at comonads and found a couple of comonads, but there are other proofs. And an example of this is where A is the finite sets and injective functions, and F is the finite sets and injective partial maps. And in that case, G is the symmetric groupoid. And so the thing we said at the beginning pops out of that. Okay. Somehow the keyboard's not changing the page for me. Right, so I want to try and use that lemma about retracts of adjunctions. So we stick with our category with a proper factorization system. And we've got this thing M going from RF to RG. And we want that to be an equivalence. But so let's assume it to be the case. And M will need to have a left adjoint in particular. So we'd like to apply our lemma to deduce that adjunction from this adjunction between J lower star and J upper star. So we'd like M to be a retract of that's short exact sequence. So a splitting of that short exact sequence we had back before would do the job. And so we want something rho from M back to J star, which is a splitting for that epimorphism. And so what that would look like, it would be something from MAB to FAB, and it's all natural in A being in G and B being in F. And so by Unader's lemma, you can take A to be equal to B and take the value of the identity and not lose anything. And so that'll give you something, you evaluate the identity, so it'll give you something from A to A over in F. And that thing's going to be called PA, and it's supposed to be an idempotent. So then you can recapture the row later once you've got the idempotent by this formula here. The row ABM is just M composed with PA. So we're just using Unader's lemma to say, if I want a splitting like that, then I need this idempotent PA. Okay, that's a bit of motivation, I hope. No, it doesn't go. Okay. Okay, so the kind of structure I want besides the factorization system is this thing I'm calling the idempotent axiom. So for each object, I want a morphism from A to A, such that it's an idempotent. It's got this property that if you compose on the right with this thing with something that's not in N, you get 0. And if you compose on the left with this thing with something that's not in B, you get 0. And it should be natural in the invertible things. And then this bottom one's the really the strong thing that it looks a bit of a mystery, but that's where we get the main theorem. That the complementary idempotent, 1 minus PA, has got to be a linear combination of things that are neither E's or N's. That seems a bit strange, but that's you want the PA to be a linear combination of things that are not E's and not N's. So the groupoid itself, if F had happened to be the groupoid, and you took E to be equal to M, then you could take PA to be the identity. And you can think of the general case as this P prime being the abstraction to the F not being a groupoid, or to the abstraction to it being a groupoid. But it does actually make it the representations the same as the groupoid, as we'll see. So this is sort of reconstructing what I said before. Now, once we've got these PAs, we get the and the P prime, which is the complementary thing. Then you get the splitting, which I'm calling pi. So yeah, you've got if. It's not much good talking about page 3. We see that that these linear functions here are in the other components of an idempotent module morphism. That's right. So this is actually working on the linearizations of the Helms, but we're taking they give modules. So this pi p prime gives you a module pi prime, a module morphism pi prime. Okay, so what do we get out of that? We get a splitting of we end up getting a module morphism from J upper star to J upper star, and then we dually get one from J lower star to J lower star. And the two things you've got to check are that, the one thing you've got to check is that they are mates of each other. And then once you've got that, you get that you have an adjunction from E to M, between E and M, these modules E and M. So now we not only have modules each way, the E and M going each way, they're adjoint to each other. And we already know that E composed with M in one direction is the identity. So you get the corollary that the M hat, because these are pseudo functors, they take adjunctions into adjunctions. The hat reverses the direction of morphisms, and the tilde reverses the direction of two cells. That's what the co means. So you get all these things in terms of actual functors now. So the M hat has a right adjoint E hat, and the functor M tilde has a right adjoint E tilde, just coming from the adjunction back in R. You're applying the hat process and the tilde process. So it turns out that the E hat is actually isomorphic to M tilde. So, because they're both adjoints, right adjoints of M hat. Now, the unit of the adjunction, the left adjoint to M, is invertible. That's the next thing you prove. You just look at what the unit is, and then you see that isomorphism I had before is the inverse of this unit. So we've got the invertibility on one side, and that's the easy direction. The hard direction that uses that last axiom on the idempotency thing is just that to get the co-unit is a split epimorphism. So you've got to really work to do that. And I'm running out of time, so I don't want to continue the details there. But you prove that it's a split epimorphism by using a bit more structure and some careful work. And this is the thing I didn't believe that Kuhn had this argument, but I had private conversations with him, and he convinced me. And so this is really just taking his argument and sort of generalizing it a bit to get this property. So that's still only telling you that the unit is an isomorphism, the co-unit is a split epimorphism. But then this is kind of like the Gabriel-Popescu theorem, where you have a sort of fullness, but the hard part is to prove fullness, and that happens. So the proof that this actually therefore implies that it's an equivalence requires a bit of work, and it's about, I can use this old paper of Brian Day and me, which is a paper telling you when a strong generator in a category is also dense, has to be dense. So in good categories like Grothendieck abelian categories or toposes, in a topos, Grothendieck topos, any generating set will be dense, in fact. You can use that, any generating set of objects of a Grothendieck topos, to be a site of definition. So anyway, there's an argument there required. And so this means that the RF and RG are actually Morita equivalent, or Cauchy equivalent in terms of V category theory. So the equivalence, under all those conditions that I've got so far, namely the factorization system plus the idempotent axiom, that's all you really need. And you get this property, and it's the equivalence is a restriction, is a retract of the restriction along J. So it is actually a little bit of, that's where the work comes. So you can replace the V by any category in which you've got idempotent splitting and finite direct sums. That's the same as the Dowell-Kahn theorem. It's not just you can take simplicial objects in any category with a split idempotence and finite direct sums, and you'll get the same as the chain complexes. This is just trying to show you how what properties might give you these idempotents. So I go into a little bit of detail there, but So I've used some notion of stiffness. Well, I didn't want to call it rigid because that's already been used a lot. But the pigeonhole principle is kind of in there. You've got that in finite sets, that if you've got a finite set, or you've got two finite sets, if they're isomorphic, then any monomorphism between them will be an invertible, and any epimorphism between them will be invertible. And the same in the finite dimensional vector spaces. So that kind of property allows you to get these idempotents that you're wanting. So the last part of the talk is meant to be about that. And this guy of originally Hungarian origin, but he lived most of his time in Canberra, in Australia, Lotzi Kovacs, actually did the work that was needed by Kuhn to prove. And what he did was to construct these idempotents in the case of the finite general linear groups. So I call that a Kovacs idempotent when you've got this phenomenon that we saw in the little baby example, where when you linearize, even though you haven't got an identity to start with, you pick one up when you linearize. And that's a funny thing that I hadn't thought of before writing all this stuff and looking into it. Yeah, so when you have that Kovacs identity, you take one minus it, and you end up with an idempotent satisfying your later idempotent axioms. Yeah. And then maybe it's all about semi-simplicity. I find I don't think we want to probably go through that now that it's 10 past. I've even gone over the hour. We started a bit late, but okay, so I want to acknowledge the fact that Alexander Campbell, my first argument needed more work, and he told me where some gaps were, so I filled them in. And for Nick Kuhn, who helped me, and Benjamin Steinberg at the City University of New York, he's got this really nice book on the representation theory of finite monoids. So I recommend that book. And a lot of these ideas, especially about semi-simplicity, are in that book. So there you are. Thank you very much for the invitation. And
well, actually, we thank you very much for this very nice talk.
I'm sorry, much maybe.
So, any questions or comments?
If there's anybody still around.
So,
yes.
Emre has question. I think yes.
Thank you. By the way, thanks for the seminar. Could you please go back to page 2 of your presentation?
Page 2?
Page 2, yes.
Yeah, okay. How do I get back there quickly? It's not very quick. No, sorry,
No problem.
I'll get back quicker. Yeah, the keyboard's not doing the job. It's taking a while on the mouse to roll it. There we go.
Thank you. My question is, categories for which there is a group G. If F were a higher dimension structure, for example, strict cubical 3 groupoid, could we talk about this type of equality, equivalence of the 3 representations?
I suppose so, yes. I haven't thought of higher examples, although I did think maybe just ordinary 2-category examples, but yes, that'd be an interesting question. I don't know. What was your setting?
Strict cubical 3 groupoid.
Strict cubical 3 groupoids, yeah.
3 gray categories, which means
right. Yeah, no, I don't know. I mean, it'd be nice to, but it's a fairly rare thing. Even, I mean, you've got to have all this structure to get even this one-dimensional case. So it's, yeah, I'd like to see some examples. I mean, you could take sort of two groupoids. There are lots of good examples of people looking at two groupoids now, and maybe three groupoids, which are obtained by taking the invertible things or the equivalences in some other category usually. So you certainly have a core arguable for each non-groupoid. So any weak three category of any type, you would have the core groupoid, wouldn't you? Or the core weak three category. But no, I haven't looked any higher than this really. But, thank you for the question.
Thank you. Thank you.
Any more questions or comments? Maybe a comment about the reference of Steinberg's book. It is indeed a very nice book. I am reading also recently because I am interested in monoid representations and monoidal schemes, which seems to be related to field with one element, what they say.
Yes, yeah. Well, the field, that's a bit of a disappointing thing about this, that the F, you've got to look at F sharp rather than the category of finite sets. You feel that the category of finite sets should work, but it doesn't work if you, so
I
that's
see.
the one element group, the one element field case. Yeah.
Any questions or comments more?
Looks like
Okay.
I've lost my.
So let's thank our speaker once more. 2 weeks later, Emre, okay, 2 weeks later we will meet again, and our speaker will be Nick Gursky from Cleveland, and I hope we will all see each other again there. So thank you very much, Ross.
Oh, thank you, Ilhan.
Yeah.
Thank you very much. I'll stop sharing screen, I suppose. Yeah. Oh, that should be interesting. Nick Gursky.
Yeah. So we have our network of communication. I also included you, and you will receive the name of the seminars and so on. But of course, timing may be very strange for you.
Yes.
Okay. So see you all later, hopefully 2 weeks later. Yeah. Bye-bye.
Yeah.
Bye.
Bye, everybody.
Yeah. Yeah. Okay, we are closing.